Well, you got the subject here. I don't know. It's fine. Better.
Yeah.
I'm all of those back and I'll go to. That is your.
Okay, first things, reminders about active. Your last two assignments are on the board. The last one is over what we're going to be doing today. I did put extra credit assignments over there. Just a reminder about Mona Lisa, if you did not pick that one up and you wanted to do it. The extra credit is due the day of the final, same with exam 3 corrections. With regards to the final exam, first thing, I have sections taking it on Tuesday and on Wednesday. If you would like to take it early, that's fine. I have room. I just need to know so I have enough copies of the test. So email me and let me know that you're planning on taking it on the 9th with my 10 o'clock section instead of with the 11 o'clock section. So, but there shouldn't be a problem with that unless the entire class wants to move their times, but I doubt that's the case. You may use either half a page front and back, like 8.5 by 11.5, and you can use both sides, or just use one side of an 8.5 by 11 sheet of paper. Put whatever you want on it, but remember, I'm going to give you the equations. So you don't need to write the equations unless what you're doing is saying, oh, use this when blah, blah, blah. Tell yourself when to use it, tell yourself how to rearrange it, those kinds of things. The final will be in 2 parts. The first part will be what I call essential skills. So that's 5% of your overall grade. It'll probably be about 20% of your final exam. So what I've been doing throughout the semester is for each quiz and test, I've been marking off what you've been showing me you can do with your significant figures and with unit analysis and some of those basic skills kinds of things. And so there will be a section that has some of that, has draw an atom and show me where the electrons and protons and neutrons are. Use the isotope symbol and tell me how many protons, how many neutrons, how many electrons. Take an equation like PV equal nRT and solve for a variable, those kinds of things. And there'll be some vocabulary on there. So that will be the first part of your final exam. There are some quizzes on Canvas in the quiz section that are labeled ES. Those are essential skill things. And you can use those to practice those scores. Some of them, for reasons I can't control, just automatically get loaded into your grade, but that's not going to be your grade because I weighted heavily. The way that the scoring ends up working is just weird. So don't worry about what the score ends up being, but you can use that to practice. The rest of it is cumulative, but there will probably be more from chapter 6 since we haven't had an exam over the last part of chapter 6. So those are things that you can prepare for. I definitely recommend using old quizzes and exams and then saying, okay, what is a different way this question could be asked? So if it's a problem, then maybe I give you a different molar mass. Maybe I give you a different concentration. Maybe I give you a different starting amount. Okay. I will not allow you to use the sliders for your stoichiometry. So you've had the chance to use sliders on quizzes and tests up to this point, but now you got to do it on your own on the final exam. So if that's something you need help with, write out on your half sheet of paper. This is what you do at each step of the way. Any questions? Okay, quick review of quantum numbers. I gave you guys this on the handout on Monday. So remember, N is called the principal quantum number. It tells us what level we're in, or sometimes called the shell. And it is, you're going to see why I say this, it corresponds to the period. It also corresponds to the size. So the bigger it is, the higher the N value. It can only be positive integers because we're counting energy levels. So we start counting at 1 and we go 2, 3, 4, so on. So L is the angular momentum. I will try to put that in a font where it has the cursive L so that you can tell that it's definitely L and not a 1 or a capital I or anything like that. This is L. We call this the subshell. So it could be the P subshell, the D subshell, the S subshell. And those tell us the shape of the orbital. The value corresponds to each letter. So S is 0, P is 1, D is 2, and that number has to be less than N. So we're going to look at a little logic puzzle here in a second. So the rule for N is that has to be a positive integer. Our rule for L is it has to be an integer less than N, but not negative. M sub L is telling us which of the orbitals we're looking at. And that can be the same as L, the opposite of L, and all the integers in between. So the way of saying that is the absolute value. Remember from math class, this means the absolute value. The positive version of this number has to be less than whatever L is. So if L is 1, then it has to be 1, -1, or 0. But this here is an L, not a 1. So when you're writing this in your notes, it doesn't have to be less than 1. It has to be less than L. Okay, so here's our logic puzzle. If M sub L, and I'm actually gonna do this. If M sub L is -1 and N is equal to 3, what values of L are allowed? All right, so let's look at N first. Since L has to be less than N, think about what are the possible values for L. Come up with 0, 1, 2. Okay. M sub L is -1. If I have an S orbital, then L is 0. If L is 0, can I have an M sub L that's -1? Because M sub L, the absolute value, has to be less than L. The absolute value of -1 is 1. Is 1 less than 0? No. So S is not allowed. Can't be 0. And so therefore, it could be a 2 or a 1. So this could be a 3p orbital, or it could be a 3d orbital, but it can't be a 3s orbital. All right. Okay, so we're going to do orbital filling diagrams. So I handed you a paper that has blank ones of these so that you can kind of fill them in rather than having to recreate them. When we fill them, what we're doing is we're putting all the electrons in. Now for hydrogen, you just put the electron in the bottom. But if we have polyelectronic, that means we have many electrons. So we have to know what the rules are. Our first rule is outbound, which is the building up principle. This says I have to start at the bottom and move up. I have to use the 1s orbital before I use the 2s orbital. I have to use all the 2s before I can get to the 3s. we're going to see that even within a level, and within level 2, there's gonna be a little bit of a shift. And so the s orbitals will always be a little bit lower in energy than the p. That means I have to fill s before I go on to p. All right, the second rule is the Pauli exclusion principle. So we know that each orbital can have 2 electrons. And so you might wonder, well, why are we limited to that? And the Pauli exclusion principle tells us why. You need to know the consequence of the rule. The rule itself is a little mathy and convoluted. Okay, so the rule says that for a given atom, no 2 electrons can have exactly the same quantum numbers. So if I have 2 electrons that are sitting in this orbital here, right now I can describe that that is on the 3rd level, n equals 3, that it's in the subshell that's D, so this is a 3D orbital, right? And I can say, okay, one of these is a 2, one is a -1, one is a 2, one is a 1, one's a 0, one's a -1, one's a -2. So I'm going to call this one 0. But otherwise, those 2 are identical. So I need some way to distinguish them. That's what the Pauli exclusion principle says. Okay. The way that we distinguish them is with the spin. Now, electrons, as the name implies, are electricity, right? And we know electricity and magnetism go hand in hand. So when I move an electron, I'm going to also get some magnetism. So the reason why m sub L is called the magnetic quantum number is as I revolve around the nucleus, as I orbit the nucleus, I'm creating a little bit of a magnetic moment. Okay, that's what that M stands for. The electrons, in addition to revolving, they rotate, they spin. So just like the Earth has night and day, spins on its axis, and it goes around the sun, it has a year, the electron does both of those things too. So it can spin clockwise or counterclockwise. And we call those spin up and spin down. So the reason why it is called the exclusion principle is because it says that each electron is exclusive. It has its own unique set of numbers. I have to be able to distinguish one from the other. So if you see the word exclusion, that's telling you that you have a limitation of labels, okay? And so our labels are going to be so that once I have found the right orbital or the door of the apartment building and somebody opens the door, I have to be able to tell the difference between the electrons living behind that door. Okay, how do we do that? You don't have to know this. This is just a where this comes from thing. If we take hydrogen atoms, because there's only one electron and then it's less confusing, and we split them up and we shoot them through a magnet, because remember, this is a magnetic number, we can tell if they respond to the magnet. Now, this is going to make sure that only the atoms that are going straight get through, because if they're kind of veering off to the top or the bottom or the side, they get blocked. So only the ones that are going straight go between the magnet. Some of them, about half of them, get pulled up towards the north. Some of them get pulled down towards the south. Okay. So that tells us some of them are spinning clockwise, some of them are spinning counterclockwise, depending on what they're attracted to. For math reasons, I'm not going to go into, the difference between these two things has to be a value of 1. And so therefore, the difference between 1/2 and -1/2 is 1. And that's why we use the halves. Okay. So our new quantum number is m sub s. So we have an m sub L and we have an m sub s. The n sub s only has 2 possibilities, 1/2 and -1/2. It can't be anything other than those 2 things. So positive 1/2 is for spin up, negative 1/2 is for spin down. Now on an orbital diagram, we're going to use arrows. We're going to draw it with arrows instead of putting numbers there. But when I ask what the quantum numbers are, we're going to add up those numbers. if you take higher levels of chemistry, then you use those halves to figure out how much magnetism a particular element might have. But for right now, we're just gonna say, is it plus 1/2 minus 1/2? Okay. So what I want you to be able to do with all of this are these things. With a blank diagram, you should be able to put the arrows in. So you're going to have to figure out how many arrows. That's going to be based on the element. And then you're going to have to show them in their ground state. Remember, the ground state is the most stable where the electrons are as low as they can be. Once we have that, what we want to do is show the, we'll have to identify what the quantum numbers are, the N, the L, the M sub L, the N sub S for those electrons. Can you share? Next, we're going to have to write the electron configuration. So you'll see what that is in just a minute. There are two versions of this. One is the complete electron configuration diagram, and one is a condensed version called the noble gas configuration, or sometimes it's just called the condensed configuration. Ideally, you would be able to then figure out if this were an ion, say it's a negative ion, so it's got an extra electron, how does that change the orbital diagram? How does that change the electron configuration? If it's positive, I have fewer electrons. How does that change things? And then transition metals have their own wonky thing that they do as well. So if you are somebody that is like thinking you're going to go to med school, or if you are going to be a physics major or whatever, you're going to take organic, you're going to take upper level classes, you might try and make sure that you can at least understand these things, looking in the chapter 6 to help you with those things. But I will test you on this first part, and I might on your exam give you a bonus question for this, but I'll test you on the first part. Okay, so this is an orbital diagram, right? And for hydrogen, the Aufbau principle says fill from the bottom up. So we put our one electron, the one arrow, in the bottom orbital, okay? For helium, we have 2 electrons. So Aufbau says it has to go from the bottom up, and there's still room in that 1s orbital. So it's going to go all the way down to the bottom. But Pauli says there has to be some difference, and that difference is going to be whether it's up or down. So we're going to have to show that second arrow as being down. All right. So that's how we do those diagrams. The electron configuration is going to tell us, without having to draw it all out, it's going to tell us which orbitals have electrons in them. So it's not going to show us the difference between each of the 3 different p orbitals, but it's going to say in p orbitals, this is how many there are. So the way that that works is you list the filled subshells, the filled orbitals. And you do that by putting N and L. So remember, that's the principal quantum number. And L is the angular momentum, the SPD. And then the number is a superscript that tells you how many electrons are in that kind of orbital. So for hydrogen that we just saw, it was in the 1s orbital, and there was only 1 electron. So we would write 1s1. For helium, there were 2 electrons. So we just changed that 1 to a 2. 1s2. Okay, so it's a shorthand way that we don't have to draw out the whole diagram. What do we do when they're in multiple orbitals? Okay, so let's take a look at lithium. How many electrons does lithium have? So the way we answer this is, remember that unless I tell you it's an ion, we assume there are equal protons and electrons. Where am I going to find protons? Periodic table. So I go and find lithium. What element is lithium?
3.
3. All right. And so Brax is already to tell me that we have 3 electrons. So I'm going to put those first 2 in the bottom, just like I did for hydrogen and helium, but the third one is going to have to move up. And I think this was the slide where I forgot to put the configuration on. Let me see. Yeah. Okay, so the configuration for this is this: 1s2, 2s1. All right. We also can talk about what are the quantum numbers for that last electron. Now we can do it for any electron, but it's easiest to identify the last one we put in. So the last one we put in was the topmost one. What is N? So remember, the label there gives us N and L. So N is 2. Thank you, Lars. What is L? So you can give me letter or number. What's the letter? It's right there. F. Okay. What number corresponds to S? 0. Okay. And then what is M sub L? And this is where we have to remember back to what are the possibilities. So for S, the only possibility is 0. So that has to be 0. For P, it could be -1, 0, or +1. So depending on which one it's in. Okay, and then for M sub S, that's the spin. This is an up arrow. So is it going to be +1/2 or -1/2? +1/2. All right. Let's see. For a hydrogen atom, so this is hydrogen, all of the S and P orbitals are the same energy within a level. So the 2s and the 2p are the same energy. And so that means if I'm moving an electron to this 2p orbital, or if I'm moving it to this 2p orbital, it's the same energy. And also if I'm moving it to the s orbital, it's the same energy. So when you're in lab this week, if you haven't been already, you're going to look at the spectrum for hydrogen. And it's going to be pretty simple because all of the lines corresponding to a transition are going to be right on top of one another. Now, this particular transition is in the UV, so we wouldn't see it. But let's say that this is the red line, okay? So that would be here. And what that's telling us is that that's actually 4 different transitions, one to each of these different orbitals. But since they're all the same wavelength, we only see one line. When we get to helium, it changes. Those are going to split apart. The S is going to split apart from the P. So here's helium. We see 2 plus signs on the bottom because there's 2 protons. As we have 2 protons, all the orbitals are going to go closer to the nucleus. They're going to sink down in energy. Right? So the ones that have the electrons and the ones that don't have electrons. When they sink, the s orbitals which exist close to the nucleus, get pulled down more. The p orbitals are pinched off at the nucleus. And so they don't get pulled quite as much. All right. And so what that means is every time we put in electrons, this is lower than this. And Aufbau says we have to fill the lower one first. We have to fill S before we fill P because S is just a smidge lower than P is. Okay. The other consequence of this is that when you go and look at the spectrum for helium, instead of having those very simple lines, we have a lot more lines. Okay, so we have splitting up of the difference between going to the S versus going to the P. And then we also have splitting up between going from this to the S to the P to the D. That's 3 different versions. Plus, we have going from the P to the S to the P to the D. Okay, so there are 6 different things that represent that level. All right. So we've talked about a couple of rules now. Which is the one that says electrons have to have different quantum numbers, that no 2 electrons can have the same quantum number? That's Pauli. Yes. It's the exclusion one. So it is exclusive. No 2 things, right? That sounds exclusive. Okay. All right. When we are putting electrons into orbitals, as we fill the orbitals, for the elements in this column, we're filling the s orbital, right? So the hydrogen, we were filling this. Lithium, we said we were going into the 2s. Beryllium is going to go into the 2s. And that's going to continue down the line. So we call those 2 columns the s block. Okay, so elements in those columns, the last electron is going into an s orbital. Over here, all of these have the last electron going into a p orbit. So you can see the p orbitals are starting to fill in by becoming more and more red. Those s electrons are already full. Okay, so that they're not changing at all, but we're putting in p electrons here. So this side is called the p block. Okay, this one is going to be the d block. We're going to focus mostly on s and p, but the middle area will be the d block. Okay, so filling in our orbital diagrams, remember that Pauli says only put 2 electrons in the orbital. They have to have different spins. Aufbau says start at the bottom and go up. We're going to run into another situation when we get to carbon and nitrogen, where we have 3 orbitals, the p orbitals, that are all the same energy level. So we have a 3rd rule, Hunt. If I have orbitals of the same energy, equal energy, so this means they're the same subshell, like a 3p or a 4d, I'm going to leave those electrons unpaired. This is because electrons are negative. They do not want to be next to each other. Okay, they want to spread out. All right, they spent too much time sharing a room with their little brother as a kid. Grown up now, they want their own apartment. So they're going to spread out. All right, so that one's the easiest to understand. The second part of this rule says we want the spins aligned. So we want them either all up or all down, if possible. Okay. So once we have enough that they have to share, then we have to have opposing spins. But as long as we can have them all going the same direction, they should all go the same direction. The reason for this is that magnetism that it's created, that as one is pointing in a direction, it's creating a magnetic field that goes in that direction. The others are going to want to line up with it. I won't ask you the why. I'm just going to ask you to fill in the diagram. Okay, so let's take a look at an example of this. We're going to look at carbon. So first thing, how many electrons does carbon have that we're going to put into this diagram? And you can use the top one on the paper I handed out to fill in this. How many electrons? So we find carbon on the periodic table. 6. There we go. If you said 6, I just didn't hear it. Okay, so Z is equal to 6. So try putting in electrons, following the rules. Start at the bottom. Only 2 electrons on each short little line. Those electrons need to be pointed in opposite directions. Then when you get to the top, the 2 electrons that go into the p orbital should be spread out. Okay, so think of these diagrams as starting a 3-part question on your final exam. So the first thing I might tell you is fill in the diagram. The next thing I might ask you is, what is the electron configuration? So that means I'm going to do the shorthand where I'm just writing these 1s's and 2p's and things like that, and telling how many electrons in each subshell. So what does the electron configuration look like for carbon? Oops. Okay, so electron configuration looks like this. If I'm looking at the diagram, again, I start at the bottom, I write the label for each level, and then I just count the number of arrows that are in that level. That's what's going to be that superscript. All right, and then the last thing I can ask you are, what are the quantum numbers? Now, I'm not going to do it for carbon, but I'll do it for the next example.
Can you tell us that you put the up arrows before you put that arrow?
In the world of atoms, it doesn't care which you do first. It is convention that most people will do up before down, but it is also completely accurate if you had both of them being down, as long as they're both facing the same way.
So how do you know it's minus 1/2? Plus 1/2?
Whichever way you drew it is what you get to say what it is. So I will look for your answer to be consistent. If you drew a down arrow, I want to see -1/2. If you drew an up arrow, I want to see +1/2. Okay, so let's look at nitrogen. All right, so let's say I was wanting to know what's the electron configuration for nitrogen. I can start by putting in the orbital diagram. Okay, so you can use another blank box on your paper for this. Find nitrogen and find how many electrons I'm going to put. 7. Then I fill them up from the bottom. Make sure they're spread out and pointing the same direction. All right. And so then I'm going to give you a multiple choice to tell me which is the configuration. So figure out from this what the configuration is. The screen's going to change. All right, so you're going to show me with fingers. A is 1, D is 4. Which one of these is the correct configuration for nitrogen? Everybody who's showing me fingers, I think most of you are correct. I see 1 or 2 that are off. So it is B. It is really easy to make the mistake of going to A. So remember, we're not counting orbitals. We're labeling it with N. So this should be a 2 because that last orbital was a 2p orbital. And even as I'm writing these, sometimes I'll just be going quick and go 1, 2, 3. So it's a really easy mistake to make. So attention to detail. Okay, so one way that we can do this configuration without doing the diagram is to use the periodic table, remembering our different blocks. So we have S block, P block, D block. And so what we do is we just follow through all of the elements until we get to the element that we're looking for, and we write using the blocks to tell us what to do. So row 1, this is why we said the period corresponds to the value of N. row 1 would be 1s, and that's completely full, so we would say 1s2. Then nitrogen's over here, so we filled this, so this is 2s2. Now we're in the area where nitrogen is, so this is 3p, but I'm not gonna put the maximum value. I'm gonna count the elements till I get there. So 3p, 1, 2, 3. So that is another way to do this. This is particularly helpful when we get to the d orbitals. All right, so notice in here, it's telling you that we go from 1s to 2s to 2p, 3s to 3p, and then we go to 4s and back to 3d. And we'll talk about why that is in just a minute. If we were going to get to the f orbitals, they would come before the d. So this block here is our breakout part that we took out of the periodic table at the beginning of the semester and stuck at the bottom. Okay. What about identifying the quantum numbers? So remember that the label for the subshell is labeled on there as 2s or 3p or whatever. That label is giving us two quantum numbers, the n and the l. So if it says 3s, n is equal to 3, l is equal to 0. If it says 2p, then n is equal to 2, l is equal to 1. I will also accept the letter. So if you're having trouble remembering which number goes with which, or you just want to be sure, you can give me the letter instead. Then when I get to m sub l, I need to label the orbitals. So I can either go minus to plus or plus to minus. So most Gen Chem textbooks do it like you would in grade school, start with the negatives and go to positives. There are reasons that an inorganic chemist like myself usually starts with a positive and goes to negative. So my convention is to go the other way. Just tell me which way you're doing it. So it is okay to write +1, 0, -1. It is also okay to do -2, -1, 0, +1, +2. Okay, either way, but label it. And then wherever you ended up, so if we ended up in this box here, we would say m sub l is +2. If we ended up here, we would say m sub l is 0. Okay. And then when you have to do m sub s, that's the spin, s stands for spin. If the arrow is pointed up, you're going to give me +1/2. If the arrow is pointed down, you're going to give me -1. Right? I will often tell you, circle the electron. Okay. And that way I know we're all thinking about the same one when we're writing these. All right. So back to our nitrogen. The red one was the last one we put in. So let's think about those quantum numbers. What is the value of n? That's the one that's written for you. 2. What's the value of L? So you can give me a letter or a number. So 1 would be the number, the letter would be P. What's the value of M sub L? That's where you would have to write in the plus and the minus and so on and so forth. So if we said -1, 0, +1, then it would be +1, right? And then the spin. Well, I guess I did have that on. So we'd say +1. And then the spin. M sub s. What's that going to be? +1/2. The m sub s can only be +1/2 or -1/2. There are only two possible values. All the others could keep increasing to infinity, but these two, +1/2, -1/2. All right, this is only in here to connect to what you're doing next semester. So this is the electron configuration diagram for oxygen. Remember that 0 energy is at the top, because that's how much energy you need to take the electron away if it were there. Since our electron is down here, we need the energy difference between here and the top to pull it out, and we call that the ionization energy. All right, now let's get into that fourth row. Okay, so at the bottom, I have 19 protons. So what element am I talking about? Potassium. So potassium should have 19 electrons. I am showing 18 of them, and I want to know where that last electron is going to go. So remember that as we have more protons and more electrons, those orbitals are going to sink down and the levels are going to split up. All right, so we have the first three levels are kind of splitting like this, but that fourth level is changing too. And it's going to change so much, the S changes so much more than the others, that it's going to come down below the 3D. And so since we fill from the bottom up, instead of filling the 3D, we're going to fill the 4S. It's a little bit lower in energy. So this is where looking at the periodic table will help you instead of just filling out all of row 3, because on the periodic table, when you get to potassium, you know you're in the S block, right? You're not in the D block until you get to scandium. So where does that last electron go? It goes into the 4S block or orbital. If I'm going to write the electron configuration, I can look at all these electrons starting at the bottom. 1s has 2 electrons. 2s has 2 electrons. 2p all together. I'm going to put all of the 2p's together, and then I put a 6. 3s2, 3p6, and then finally 4s1. Or I can follow the periodic table and say, okay, potassium's there. I'm going to start at the top. First row is full, so 1s2. Second row, 2s2. 2p6, 3s2, 3p6, and then I'm down here at level 4. So this is where we said n was equal to the period on the periodic table. N is equal to 4, 4s1. The one place that's a little bit wrong is that our D block is shifted down 1. I'm not going to ask you transition metals, so you're not going to have to worry about that, but that's why they're a little bit weird. All right, so how do you remember the order? Sometimes you'll see diagrams like this. We have one over there that's very similar. Sometimes you'll see these crazy things. I have one that kind of looks like a Christmas tree, sort of on its side that shows you all of these. But as I said, I think the easiest thing to do is follow the periodic table. Okay, that was a lot to write with potassium. We don't want to always have to write all of those out. So sometimes we will write a noble gas configuration or a condensed configuration. So how do we do that? We find the noble gas that is before the element that is the heaviest. So the noble gas before lithium is helium. The noble gas before potassium is argon. So we just did potassium. We just had that configuration. So we would pick argon. We're going to put that in brackets. That's basically saying all of those are core electrons, and core electrons don't do anything. They're not going anywhere. I don't care about them. I'm just going to put them all in this box, and I'm going to say they're the same thing as argon. The core electrons for potassium are the same thing as argon's electrons. Putting them in that box. And then I just write out the configuration for the valence electrons. Okay, so the only thing after argon was that 4s1. All right, so for each of these elements, it would look like this. And what this shows us is those valence electrons, boy, they sure look a lot alike. And that's how we get similar group properties. Okay, last thing I want you to do is look at that paper that I handed you that says quantum numbers at the top, and then it's got magnesium and an example. We're going to look at phosphorus real quick. We'll walk through phosphorus, and then I'll give you the answer key on Canvas so you can check yourself, but go ahead and try those for yourself. All right, so phosphorus is element 15. And so if we wanted to write the electron configuration for that, we could follow on the periodic table. We could say, okay, it's in row 3, but I'm going to start with 1s. Or we could fill in the diagram, and you can use the bottom part of the blanks ones that I gave you to fill these in. Now, one thing we have to remember is when I get up here, I've only got 13 electrons. Can I put the next one like this? Is that allowed? No, because I want to spread them out. They don't want roommates. Okay, can I put the next one like this? No, I want them all aligned. All right, now if I put a fourth one in, it has to be paired, it has to have the spin down, but right now I don't have to do that. Okay, so the electron configuration is going to look like this. If I do the noble gas configuration, I need to figure out what is the heaviest noble gas before phosphorus. So is argon before phosphorus? No, it has 18 electrons. So I'm going to go to neon. Neon will be in brackets. And then I'll put 3s2, 3p3. That's what's going to go in this box. All right. Now, to draw out the configuration, we put this here showing you the three up arrows. So you know whether it's up or down and what the M sub L is going to be. So what is N if we're in this last set? What is N? 3. What is L? It's not 2. It's 1. Or P is okay for me. All right. And then if I put -1, 0, +1, M sub L is going to be +1. And then what would M sub S be? Plus 1/2. All right. So I will put answer keys for that on Canvas. I will follow the conventions of going negative to positive, but if you reverse it, it's okay.